In the second approach, let's try to use advanced graph theory. Depending on how much graph theory you know, there is a better definition for us to determine whether or not a given graph is a tree. So for a graph to be a valid tree, it must have exactly n-1 edges. So any less edges than this, it can't possibly be fully connected, and any more edges than this, then it has to contain cycles. So additionally, if the graph is fully connected and contains exactly n-1 edges, then it can't possibly contain a cycle, and therefore it must be a tree. So going by this definition, our algorithm needs to do the following. So first, we just check whether or not there are n-1 edges. If there is no n-1 edges, we just return false. And then we have to check whether or not the graph is fully connected. We will return true if it is fully connected, and we'll return false if it is otherwise. And let's recall the most complicated part of the first approach was in the checking whether or not the graph is contained cycle. This is because in an undirected graph, we need to be very careful with the trivial cycle. We have to check whether or not graph is fully connected. It is straightforward. We just simply check if all nodes were reachable from a searching starting at a single node. And like before, we can check for connectivity by using recursive depth first search, or iterative depth first search, or iterative breadth first search. So if there are indeed cycles, we still need to use a thin set to prevent the algorithm getting caught in an infinite group and to prevent looping from a trivial cycle. So first, let's try iterative depth first search. We first set a stack which have 0, and we mark 0 as a sin in the sin set, and then we pop 0 from the stack, and we checked when the node is 0, it had an adjacency list at 0 which have 3 neighbors, which is 1, 2, 3. Now first we check when neighbor is 1. We never see 1 before, so we add 1 into the sin set and append 1 into the stack. And then we check when neighbor is 2. We never see 2 before, so we add 2 into the sin set and append 2 into the stack. And then we check when neighbor is 3. We never see 3 before, so we add 3 into the sin set and then we append 3 into the stack. So now we have finished the for loop for neighbor in the adjacency list. Now let's start popping. First, we pop the 3 from the stack, and it will check when node is 3. It has a neighbor 0 which is in the sin set, so we continue to skip it. And now let's pop 2 from the stack. It will check when node is 2. When node is 2, the neighbor is also 0, which is also in sin. So we keep popping. Now let's pop in 1 from the stack. It will check the node 1. When node is 1, it have 2 neighbors, which is at the adjacency list at 1 is the neighbor 0 and 4. Now first let's check when neighbor is 0. 0 is in sin before, so we use continue to skip it. Now let's check when neighbor is 4. We have never seen 4 before, so we add 4 into the sin set, and then we append 4 into the stack because we already finished the for loop for neighbor in the adjacency list at 1. So we have to pop 4. Now we check when node is 4, it have a neighbor 1 which is seen before. So we are finished. After finished, we have to check the length of the sin set, which is 5, which is equal to n nodes. So that means we already checked all of the nodes. It is fully connected, so we have to return true. So first, we create a sin set, which contains 0, which that means what we have already seen. We still need this sin set to prevent our code from infinite looping if there is a cycle or any trivial cycle. And then we create a stack. The stack is the node we want to check for later. And then let's start. We'll create a while loop. While stack exists, every time we pop an element into a stack to the node, stack.pop, and then we check this node by for neighbor in adjacency list at node, and we check if the neighbor is in scene. That means we already seen them before. Then we just continue to skip this neighbor. And if this neighbor is never seen before, we just append the neighbor into the scene set. So it marks as a scene. And then we append the neighbor into the stack. So we will check them later as a node. And then after we finish this while loop, we just return the length of the scene. We compare the scene set, which is we already seen node, with the n. So if the n is equal to the length of the scene set, that means we already check all of the node. Then it will return true. So now let's run depth first search for node 0. The node 0 is never seen before, so we put it into the scene set, and then we check its neighbor 1, 2, 3, which is adjacency list at node 0, and then we run depth first search for the neighbor 1. So the node is 1, and we never seen 1 before, so we put it into the 1 into the scene set. Now let's check the neighbor of node 1, which is adjacency list at 1, which is the neighbor 0 and 4. Now let's run depth first search for node 0. The 0 have been in scene before, so we return. And now let's keep check another neighbor 4. We run depth first search for neighbor 4. We have never seen these 4 before, so we write them into the scene set. Now we check the neighbor of node 4, which is 1, and we use depth first search for this neighbor 1. Then 1 is in scene before, so we return, and we keep searching depth first search for node 2, and 2 is never been seen before, so we write them into the scene set. And we then check the neighbor of the node 2, which is 0, and we run depth first search for this 0, which is in scene before, so we return, and then we check depth first search for node 3, and 3 is never seen before, so we write 3 into the scene set, and then we find neighbor of the 3, which is also 0, and then we run depth first search for this 0, which is in scene before, so we return. And then we check the length of the scene set, which is 5, which is equal to a node. So it will return true. That means we already checked all of the nodes and it is a valid tree. So first, let's define a scene set, which is an empty set. And then let's define depth first search. It have a node variable. And then let's check if the node is seen before is in the scene set, then it will return. So it will finish this algorithm, finish this function. And if it's not seen before, we add them to the scene set, add a node into the scene set. And then we use a for loop for neighbor in the adjacency list at node. It will iterate every neighbor by depth first search. We recursively call it by neighbor. And then we use depth first search for node 0. And after finish them, we should compare the return, the length of the scene set with n. If it equal to n, that means it is a valid tree. It returns true. So first, let's create an array Q, and it have element 0, and we create a scene set. It also have the element 0, and then we pop left 0 from the queue, so it will check the node 0. The node 0 have a 3 neighbor, 1, 2, 3, which is adjacency list at 0. So first, let's check when neighbor is 1. When neighbor is 1, we never see 1 before, so we add 1 into the scene set and append 1 into the queue, and then we check when neighbor is 2, and we never see 2 before, so we add 2 into the scene set and append 2 into the queue. And when neighbor is 3, we never seen 3 before, so we add 3 into the scene set and append 3 into the queue. So after we check the neighbor of the adjacency list at 0, now let's start pop. First we pop left 1 from the queue, and now it will check when the node is 1. When node is 1, it have 2 neighbors, 0 and 4, which is adjacency list at 1. So now let's start check when neighbor is 0. When neighbor is 0, 0 is in seen before, so we use continue to skip it, and it will check when neighbor is 4. Because we never seen 4 before, so we add 4 into the scene set, and then we append 4 into the queue, and then let's pop left 2 from the queue. So it will check when node is 2. When node is 2, the neighbor is 0, but 0 is in scene before, so we use continue to skip, and then it will pop left 3 from the queue, and it will check when node is 3. When node is 3, the neighbor is 0, and 0 is in scene before, so we use continue to skip it. So now let's pop left 4 from the queue, and it will check when node is 4. When node is 4, it will have a neighbor 1, but 1 is already in scene set before, so we use continue to skip it. But now there's no more element left in the queue, so we have to finish this function, which is check the length of the scene set, which is 5, which is equal to n nodes, so it will return true. It is a valid tree. So first, let's create a scene set. First, it have 0 element, which is marked 0 have already been seen before, and then let's create a queue. A queue is a collection, and first we dequeue the 0 into it, and then we use a while loop. While queue exists, we update our node by pop the element from the left from the queue into the node variable, and then we use a for loop for neighbor in node adjacency list as node, and we will have to check the neighbor. So if you check whether the neighbor is in the scene set, if in the scene set that's already been seen before, if it already been seen before, we use continue to skip it. If it not been seen before, we add them into the scene set. We add the neighbor into the scene set, and then we append them into the queue by append the neighbor into the queue. And after finish this while loop, we just return the length of the scene set and compare it with the n. If it equal to n nodes, that means we already checked n nodes. That's return true. That means it is a valid tree.